Okay, I think we can start now.
Okay. Good evening,
So,
everyone.
yeah,
Good evening, sir.
good evening and welcome back.
Yes. Welcome back to the evening session of day 5 of our short-term training program on quantum technology, applications and implications organized by Department of Physics, Assam University, Silchar. We are pleased to have Professor Pankaj Dev Sharma with us once again. And we now continue with the second lecture in the series on Introduction to Quantum Artificial Intelligence and Machine Learning, which Professor Sharma will be delivering as a continuation of his earlier session. So without further delay, I invite Professor Sharma to kindly begin the session. Sir, please, the floor is yours.
Thank you. Thank you and welcome back again, everyone. I hope I could reach everyone's understanding to a good level yesterday when I spoke on the introductory session about quantum computing, summarizing, then moving over to artificial intelligence, and then to the prospects of quantum artificial intelligence and its goals in future. So continuing with that, as you know, now coming over to the second part of the proposed session, in which we'll talk about machine learning, a core component of artificial intelligence as it has evolved over the years. And in preparing today's session, I have referred to many review uh, papers as well as articles coming out from NASA in the in its own report, in its report in around 23, towards the end of 23, and setting it into the current horizon in which certain works are going on. And at the same time, I have tried to avoid the mathematical details of the algorithms and picking on those things, and mostly the concentration which is uh, being looking up to in recent times and for the future. So, one of the striking technological developments in the early 21st century is the measuring of artificial intelligence, as we have already understood, observed, and experiencing at this moment. And this happened, as we just recollecting, after worldwide research since 1950s. And intelligent technical systems have now become a reality thanks to advancement in quantum electronics, VLSI, and many such things. And they are getting deployed. We are experiencing all of them. Some of the examples with which we are familiar present day scenario are cognitive systems for robust text and speech recognition and generation, which we are all accustomed to experiencing with ChatGPT in large language models, LLMs, and many such other versions of the ChatGPT chatbot and many other things. Image and video understanding and synthesis, in which various aspects of image and video understanding has been dealt, from recognizing to matching, identifying, as well as cross-examining and everything. Game playing is one of the oldest problem with which AI began, and it continued with machine learning. Game playing algorithms and software are becoming more robust and powerful as of now than recommendation or recommender systems in many domains, from books, movies, business prospects, investments, and many such things where recommendation systems are required and it become a reality. Medical diagnosis, uh, which was there in the form of expert systems in the in the past, in 1970s on around. Subsequently, machine learning AI advancements has led to increasing emphasis on medical diagnosis and related domains, and it has been evolving and maturing very fast at this moment. Then planning, decision making, and so on. So then, what is machine learning? It's a branch of artificial intelligence, and present day artificial intelligence achievements are attributed to this machine learning because it happens to be the core or kernel of an AI system in a sense. And the recent performance boost in AI products is due to such systems which learn an intended input-output behavior from analyzing task-specific example data. So talking about task-specific example data, for example, if we have to recognize a particular face of a person entering in an office instantly, so that means there are such images are stored, and the images of the person is also stored in a database, and then it is to be matched, and it is to be matched in a specific way that so that it cannot be in a sense duplicated wrongly. So there are a lot of security aspects behind this. So this is a specific task in which entry of a person has to be automized with all security cross examination systems has to be automated. So such other things. If we have to employ machine learning technique for uh, predicting the behavior of a particular uh, stock market situation at a given point of time, how much data is necessary for predicting that, and these are such kind of task specific example data. So there is uh, generality as well as their specificness in the data, and that depends. We'll come back to all this in the following discussion. Machine learning then now concerns with adjusting. Now coming back to the little bit of next, it is about adjusting parameters of a software system in a training process such that it can develop cognitive capabilities, and these parameters are basically expressed through mathematical functions. So these parameters are now in a quantum computing setting, the parameters will be enlarged, number of parameters will increase very high, and this adjustment of parameters are very much essential. And now now question comes, who will adjust these parameters? A human intervene, a person, I mean, interacting with the software, or automatically? Ideally, it has to be automatic adjustments, but at the same time, human intervention are also necessary, because in the end, the human will judge the appropriateness of the learning and the training process, learning through the training process which is undergone, and has the software has developed cognitive capabilities so that it can recognize a particular human face and so on. Machine learning was originally conceptualized by Alan Turing, as you mentioned, past, and the boom period began in 1990s simply because the computational cost and the involvement of the data in the machine learning algorithm execution are tremendous. And also it is proved and experienced that the more the data in training, the more perfect will be the outcome. So therefore, it necessitates powerful machines, high performance computing systems, and therefore naturally the boom period has begun after 1990s because of the obvious reason of the advancement in the electronics and hardware industry. So, and this also has got to do with the algorithms for training. The artificial neural network become available because AI, as you mentioned yesterday, suffered a sluggish period between 1960s to 1990s, late 80s up to, because of the same reason. And so once the neural network research advanced, the perceptron based and back propagation, then following up the ability to learn long-term and short-term STM and LSTM devices has been put in place. Also, the chips with embedded neural networks has started happening. So obviously, the boost has occurred. So, of course, now as of now, we have got tremendous development in this with the help of, deep learning as well as convolutional neural network and many other variants thereafter. Now, where it stands together, quantum artificial intelligence and machine learning. So exponential growth of data and use for training. So the data growth has been tremendous, and these are used for training uh, in recent times. So sources are social media platforms, mobile communication devices, digitization of industry and life, natural sciences like life science and so on. Just 1 minute, quick break, please.
Sir, you are not audible.
Hello, Pankaj. Hello, Pankaj, you're unmute.
Yes, it's okay.
Okay.
Fine. So I'm just continuing a quick happening just a moment. So what happened is this exponential growth of data, which are used for training, has come from different sources. So these sources could be from social media platform, what we have a lot of data gathering every moment, mobile communication devices, digitization of various industries where data is automatically getting accumulated, natural sciences data, data from the satellites which are getting accumulated readily and streaming into the devices. And so therefore communicating as well as learning and executing those data for discovering the patterns within it through automated learning has become a much needed, it become a foremost necessity as of now. So therefore, what happened in order to provide this kind of capabilities, provide this facility, what it required, increasing capability as well as decreasing cost of the high performance computing hardware. So it is almost 15 years since the availability of the graphics processing units for computing has emerged as a substitute for the conventional CPUs, and in order to apply for such serious applications. So rapid, it is along with that the rapid development and availability of the OS open source software for design, training, and deployment of ML systems. This is another tremendous setup actually, which came into existing with the concept of Linux actually as an operating system. Since then, the open source software platforms have been growing rapidly, and it has been a sort of a movement that we, for software, don't have to wait for someone's proprietary things, proprietary development efforts. It is a evolutionary trend in which the software are available openly on the internet, and we can use it, apply it, and also further develop the software in a better manner. Then the progress in neurocomputing through deep neural network and deep learning all have added to the evolution of machine learning as it stands at present. Now, what are the present concerns? So the present concerns actually towards the limitation that we have at present, and how these present concerns actually lead to a case for quantum machine learning situations. So for producing results which can be treated comparable to human-like performance in training and prediction, the underlying mathematical models require more flexibility and thus more adjustable parameters than at present. Because the more the parameters which will have to be adjusted, the more will be the computation, the more will be the iterations, and at the back end, the amount of data is also increasing in a voluminous manner. So all put together, there will be more computational requirement on the present day systems. So that is one concern. Even the high-performance systems are not readily available for everyone. It comes at a higher cost. So one example we can have here is that the adjustable parameters for an artificial neural network are its synaptic webs. So in case of a neural network, the adjustment has to be done in the synaptic weights, and the modern deep neural networks provides hundreds of billions of such weights in the deep neural networks. So such flexible models must be trained with large amount of training data, because more the weights, more the weights, the more data will be required. Otherwise, if it is trained with just a few amount of data, then it will not learn anything. Of course, the generalization that is expected from the learning is not going to happen. So training of modern learning systems is thus a resource-intensive endeavor, which translates to several hundred GPU years of computational time. And the computation time, as you see, has to be happening in few seconds, if not in minutes, if few minutes, if not in seconds. So therefore, or even lesser time than that, in training large volume of data. So it is a resource intensive, and these resources are software and hardware resources and the data. Modern machine learning has therefore reached a point where practical feasibility and success are conditioned on access to HPC hardware. If we do not have HPC systems, we are not in a position to actually training a feasible machine learning system which can be practiced and applied. Machine learning researchers need to look for another technology, therefore, and this is for making sustainable progress. So the way it is, HPC systems will prove to be inadequate in time to come. So where would be the possibility? It is in quantum information processing and quantum computing. So this leads to what is the position of quantum computing in all the three situations. Three situations is quantum hardware, quantum algorithms, and quantum data. So in this situation, we have, as far as quantum algorithms are concerned, we have source quantum algorithm, devised or designed in 1994 by Peter Shor, as we discussed last time, for large integer factorization, which was successful in providing exponential speed up over classical approaches, in which the classical algorithm, the best known one, is the RSA algorithm, cannot solve this problem in polynomial time. So this problem was solved in polynomial time on a quantum computer. So this is one of the attention for success of quantum computing. So this discovery implied that common data encryption schemes, which is classical in nature, would no longer be secure if quantum computer becomes a technical reality. So this is a threat, at the same time an opportunity as well, because the threat will also have to be perceived through quantum computing, and therefore there has to be a approach of preventing the threats to quantum computing as well as securing it through quantum computing. Second method, which is very much required for search over the data sets, large data sets and all, is Grover's quantum mechanical algorithm for database search. Just followed Peter Shor's algorithm in 1996, this one, and its variant, Grover's amplitude amplification algorithm. And it demonstrated that quantum computers can exhaustively search unstructured lists in quadratically faster time than digital computers. And this is crucial because in machine learning, we have to search through a huge space of data covering billions of terabytes and above, exabytes and above the range of that. So therefore, these two pioneering contributions and the present research developments in the domain has demonstrated that quantum algorithms running on ideal quantum computers, this is the precondition, would indeed exhibit quantum supremacy, which we discussed yesterday, while dealing with certain difficult problems. And it also made clear that quantum supremacy would have considerable practical implications in terms of uh, getting the desired results and the systems for deployment. So the condition here is that we need to have physical quantum systems. So this observation of quantum supremacy, therefore, has made the development of quantum computers of industrial strength as an engineering problem rather than a fundamental research problem. Fundamental research in this domain is also going to go on happening and progressing. At the same time, designing systems as an engineering, from an engineering objective, is also taking place. And in this context, in last December, Google actually announced their latest uh, quantum machines of around about 2000 qubits in D-Wave system 4, and which is, they are claiming they have achieved uh, quite a high speed up for executing problems, which, as per their observation, would have taken more than the age of the universe as on it today if computed on a classical computer. Of course, about this, there are a lot of debates happening, and the result of these debates will be leading to maturity of the proposals itself. So this is the state of affairs at this moment in case of the quantum reality. Now, many of the fundamental problems in machine learning require optimization or search problems. Optimizing on the dimensions of the data, optimizing on the search patterns, optimizing in representation, and many other such things. And therefore, at the same time, QML research is also intensifying both in academia and in the industry, so that a feasible solution for the problems that are envisaged at this moment are going to happen. So against this backdrop, a prediction is this, that the quantum machine learning on reliable large-scale quantum computers will soon facilitate demanding learning tasks and even put the problems of uh, put the problems into reach, which are intractable and or hard on digital computers of present day situation, that is the classical computers. So therefore, this is an essential requirement, and quantum technology, which in turn is core of AI, will further accelerate the progress of AI. Now, a little bit of risk involved in this context. Since learning systems are commercialized and there are industrial deployment even in sensitive areas like autonomous driving, financial services, therefore, questions about their ethics, reliability, trustworthiness, and safety, these are also becoming more urgent than machine learning as an academic endeavor. Here also, automation and the algorithmic development is required so that these concepts, these properties can be involved, can be embedded in the final product when deployed. So therefore, as machine learning and quantum computing are now beginning to coalesce, coming together, therefore, this question shall be even more important in the research of quantum AI/ML. Alternately, the expected impact of QML on capabilities and utilizability of artificial cognitive systems, it is appropriate to assess the potential security issues related to QML. So one way, the advancement of quantum AI/ML, at the same time assessing the potential security issues and the risks together so that it can move hand in hand without having a gap. Now coming over to the situation of, in case of machine learning situation, we have different types of machine learning techniques, as we know. But in case of quantum computing, how can these machine learning algorithms, which are all classical in nature as of now, can be grouped? So first are quantum inspired classical algorithms for classical data. So the data on which quantum systems, quantum algorithms will be executed. So there are constraints like the way data we have, these are not quantized. So therefore, are quantum algorithms capable of executing on this data, executing this data? So the answer is yes and no both. So therefore, the first category developed is quantum-inspired classical algorithms for classical data. In this case, data will remain classical, and the classical algorithms will be improvised through quantum computing concepts, so that the learning will get better. Then second, genuine quantum algorithms for classical data. This is actually an abstract form of physical aspect of hardware of quantum computers. So genuine quantum algorithms as of now is basically hardware systems. It is not coming outside to the domain of developing programs. So these are in a sense embedded situation. And such things, how are these executed on classical data sets? Then converting the data to quantum data sets so that the classical algorithms can be executed on quantum data. And finally, the quantum algorithms for quantum data. So this is a taxonomy as well as a roadmap for development of such uh, kind of algorithmic possibly algorithms for computing with quantum systems. In continuing with that, the situation we can just broadly represent like this, the four types of quantum algorithms. So classical algorithms with classical data, first left box, classical algorithms with quantum data, CQ, quantum algorithms with classical data, and quantum algorithms with quantum data. So classical ML is an example. Suppose if we take an example here, so classical machine learning example is one deep learning method, deep learning neural network. So if we do, this is classical algorithm on classical data, which is outside the quantum domain. Now machine learning on classical data using a quantum computer, that is a CQ. Sorry, yeah. So classical data, quantum computer algorithm together means we are running a classical algorithm on a quantum computer and using classical data while computing. Then data set is changed to quantum data sets. Algorithm remains classical, means like a conventional deep learning algorithm, and see what results it is going to produce. Are these results going to be better than this or this? And finally, combining quantum data and quantum algorithms together and running. So performances on these computers now at present, these are in miniature form, can be done through subscription, of course, on IBM as well as Google quantum systems for time slice that they are allocating through subscription, and it can be done through Qiskit techniques, Qiskit platforms. Now, in this situation now, algorithm design is a major issue for quantum machine learning development or progress. So it is still a very much a theoretical endeavor, and many theoretically valid ideas. This is the reality, that many theoretically valid ideas cannot be implemented on present-day quantum computing devices. For example, take the source algorithm. It is till last report that I read, it could only factorize 15. So therefore, the number 15 is factorized by using source algorithm on a quantum device as we have today. So therefore, this cannot be taken example of its failure, but rather the system that we have is not in a position to do things better than that. But with time developing the system, it will be able to factorize a larger number than that. So that is a theoretical possibility. So based on this kind of, uh, algorithm, the further algorithm for machine learning will get developed. So which actually mean therefore is physical hardware aspects are to be kept in mind while assessing the validity of the proposed QML solutions. So this is a reality which will move on for a long time. And we can also observe when we talk about present day systems, the bare machine, that is the hardware, is actually covered up with a lot of layers of software in order to help us provide us with the user friendliness and ease of executing the tasks that we intend to. So when we have a completely quantum hardware device, then all these software layers will have to be existing there so that to provide us the ease of practicing as we have today. So until then, whenever such development is taking place and the efforts on, we have to just have it compared in respect of or with respect to the physical hardware aspect, physical hardware availability, and keeping that in mind, the proposed QML solutions are to be designed. Secondly, there is the other case, that is data pre and post processing situations. So the data that we have it is not possible in classical systems, not even going to be possible in quantum systems. That data as we collect cannot be executed straight away. It needs to be pre-processed. So pre-processing of the data involve multiple steps in order to make it perfect for computing, because the in collected data contain noise. So unless the data is noise free, the results will not be appropriate and it will happen properly. So then once the data is pre-processed, made perfect and computed, results will come, and the results will have to be also to be presented in an understandable manner so that the stakeholders and the programmer and the user gets to know what has happened, what is the outcome. So that involved the post-processing efforts, designing and presenting the post-processing systems. So that is the thing. Then against the algorithms have to be robust against noise. Then the number of available quantum bits that is qubits for computing. And then the quantum circuits necessary and the complexity of these circuits. And then over and above the reliable, how these assumptions will be reliable in the context of currently proposed QML solutions. So these are some of the issues that designing quantum algorithm for ML has to be taken into account. Broadly, there are many more, but still these are some of the presently important situations, important aspects that is to be undertaken while designing quantum algorithms. So even if the current quantum systems have a large number of qubits, then also they are not able to be put to use, because as a single qubit system needs dozens of other qubits in order to perform the error correction, because noise is a considerable occurrence of noise is a considerable hindrance in the presence of quantum computing scenario today. So now, coming back, machine learning is the science of fitting parameterized mathematical models to data. So while computing with machine learning techniques, what is done that the parameterized mathematical models are fit to the data in order to realize intelligent systems that can make predictions and draw inferences. So this data can be of different types: numeric, text, images, and so on. So, for example, if we consider like uh, given a set of weather parameters, very few, like the temperature of the day, humidity level, then the weather outlook, whether it is sunny, rainy, etc., and whether there is wind or how strong it is, wind is strong, weak, or medium, etc. Such kind of data, let us say, given. And we have the system, the machine learning system has to learn to predict whether a particular game is possible in these circumstances or not. That means by finding the weather data, the player will assess whether a game of golf, let us say, can be played in such a scenario based on these 4 parameters. So what is requires, therefore, it requires a mathematical model to compute with this given data. And the size of the data, of course, we are not saying it can be any number of rows. We are collecting them as rows in a tabular form, with every vertical column representing the weather parameter. Now, once such data is given, the job of the machine learning program is to predict that getting the input weather parameters, whether game golf can be played on this day or not, or at this time of the day or not. So how to do it? There are many ways. That means the parameter as mathematical models to be fit in. So one of the classical way in which such problems were initially done, this is the classification problem. Through classification, this can be predicted. So the task of classification actually is designed on the concept of entropy. So the thing which is gone into that in collecting those data, basically these data sets are containing random occurrences of weather behavior patterns. So therefore, data is sufficiently random, and therefore it is not losing any generality. So therefore, a statistical model with calculation of entropy can be done, and the entropy tells how much randomness is the data is available, is existing in the data, and against which every parameter, that is which is to be finally adjusted, is how much information every parameter is carrying. So therefore, two things: the mathematical function is designed for what is called information gain, and the maximum information gain is actually calculated for each of the parameters by subtracting the entropy involved with that parameter in the entire database. So total information will be total entropy of the entire data set, subtracting the entropy with respect to a particular parameter or the attribute of the data set, and then the information gain is calculated for that particular parameter. And then this is repeated for each of the parameters in the given data set, and then the parameter which is giving the maximum information gain, that is considered to be the root of the decision tree. It is a nonlinear tree-based structure in which the parameters will be fitted, so that by constructing this decision tree, a set of rules can be formed, if-then rules. If, let's say, weather is sunny, rain is no, wind is moderate, play yes. So this kind of rules based on the computation can emerge. So when these kind of rules have been organized in the form of a tree, this is called the decision tree, and based on this decision tree, all the rules can be expressed as a disjunctive of as a disjunction of conjunctions, so that any input parameter value will be fitting to one of the rules, and it will lead to one of the conclusion, and that conclusion will be actually on the leaf nodes of the tree. So there, this the parameter fixation has come into getting the more appropriate modeling. So this whole thing is called modeling of the machine learning, a machine learning model. And this requires training, that how perfectly the model can predict, because when the outcome will be generated by constructing the decision tree, the job of this training data is over. Then if the training, if we are satisfied with it, then it will be deployed for predicting the current situation. So current situation data will be, so suppose today at 11 o'clock, this was the weather parameters, this was given to the system. System says, okay, go and play. So that is the reliability. That is, and if the person goes out and finds it is raining, then of course the system prediction is failing. So therefore, the reliability aspects requires further training. So therefore, the data on which this training is performed has to be general enough. It should be representing the entire scenario as generally as possible, as widely as possible, and also it should take into account all the possible parameters without repetition. And also there has to be other aspects like the data on which the system will be trained. This should not be having skewed representation, means skewed outcome. The data will be actually labeled. Every row of this table will be labeled, that is based on the data whether the game is to be possibly played or not is marked. So while on this training data, if the number of instances means every row of the data has got a sufficient number of true as well as sufficient number of false. I'm talking about only true and false kind of machine learning situation, that is binary decision, yes or no. So in that case, the number of instances representing yes, that is play is possible, and the number of instances saying no, that is play is not possible, should both remain balanced. If there is imbalance in the representation of the data, the decision is likely to be skewed because entropy will be different, and as a result, information gain will be calculated differently for every parameter, and the rule that will be followed from there will be different. So it will lead to a different prediction, wrong prediction. So of course, this is called balancing. We'll come back to this in once again subsequently. So this is a machine learning scenario in which parameterized mathematical models in the data has to be designed so that intelligent systems can be developed, and it is capable of making predictions or draw inferences. There are many such techniques in machine learning, like this is one I mentioned. There are regression, there are logistic regression, k-nearest neighbor methods, decision tree based number of enhanced algorithms like random forest and so on. Then of course deep neural network, DNN, and so on. Now, how to represent a data set? This is just one simple way of putting it. A data set is not a conventional database, first of all. It is a combination of many things, numeric, non-numeric, text, and all that. So any individual data object, therefore, can be encoded in terms of a tuple, that is a row of a table having multiple columns of m real numbers. Here we are talking about numeric entry zone, the numeric data only, that is in the real number situation. But once again, all data cannot be put into real number. That these are again some other situations, like when we deal with data which are not numbers, how to compute them. What other alternatives are existing? So data in general, which are numeric, can be computed straight away, but which are non-numeric, how to make them numeric if required, or otherwise what alternative we have in order to process. So here in this case, we are considering as a m real number, that means m in terms of a tuple encoded the m real number, and let x be the tuple representing an m dimensional data point. So this m represents the dimensions of the data. So the dimensions of the data is represented in terms of number of columns in the table. So normally we are familiar with dimensions up to 3 or 4, but in this case, data can have multiple dimensions. So therefore, the the abstraction in which a data set D is represented as a collection of n data points. That means n data point means there can be n number of rows with with small m number of columns, and each of the n number of each of the x's here, xi's, representing one of the rows in the n dimension in the m dimensional data set having n having small n instances. So small n number of rows, m number of columns, every x represents one row in the table. So that is how we can abstractly mention the data set capital D to be a collection of a collection of n data points, and we put it in this form. Of course, we are not going beyond this. So now beyond this, then there is another concept of the annotations in the data, that is the metadata. So this is the information about the data, because when we store a real number, what this real number is about for a particular parameter, that is to be encoded. So, and this metadata is actually annotated by, data is annotated by the metadata, which contain additional information about the data. So example, when a photo is taken, its timestamp, what time it was taken, what is the location in which the photo is taken. A caption is added to describe the content of the figure. And similarly, the resource description framework, the RDF of the website. And as we all understand, ISBN number of a book, that is also contained in the metadata of the book. So therefore, metadata can also be expressed as a pair of label data set. Like, so it is, suppose if Y is about this R1, about a particular data set, then the annotated data set will be of this form. For each row X1, there is a Y1. Y1 is the set of metadata for row X1, and likewise for the entire data set. And this is a labeled data set. So likewise, the data set has to be made ready in this for computing. So data set is so vital that unless the data set is proper, the machine learning algorithms will never produce a reliable result. So it is the source of all information about a specific domain. So the data which is collected in a certain context or form are not arbitrary. They are actually the real one, and they are collected for real execution. So in machine learning, it is expected that the application-specific data set exhibits certain regular. Now, while in machine learning, in machine learning, it is expected that the application-specific data sets exhibit certain regularities, which may be intricate or complex and are not obvious to human analysts. So this is the situation that the data as we collect in a tabular form or any other form or any other structure, as the data grows in volume, then unknowingly within the data, lot of regularities or irregularities, or in general, if we can say pattern, develops, which are not visible straight. It is something like if somebody does not know how to play a game of football, soccer, and the person is exposed to the game repeatedly without being told. After a certain duration, he has been asked about the game, that what he has seen and learned. Definitely there will be good amount of answer. So this is the situation in machine learning too, that the data set is something like a game that we are observing without knowing its rules. But then we are trying to discover the rules which are developing within this data. So that may be intricate or complex and are not obvious to human analysts. Now, the analogy here again extended, and from this, the regularities may be complex, or at times it may not be visible, or rather not visible to human analysts. We require the programs and algorithms to compute. So any machine learning solution, therefore, for a real world problem implicitly mean that there exists some generally unknown process or mechanism which can exploit variations in appearances within a sample of data. So this is the expected solution for a real world problem, that the unknown process or mechanism which is to be exploited in order to bring out the pattern that is existing within the large data sets. So therefore, mathematically, if we assume that there exists some function small f, which belongs to a larger family of functions capital F, with parameters some theta belonging to a capital theta, which models the aligned as well as the latent characteristics of a set of data. So then, coming to the case of labeled data. So as you said, labeled data, if we take the game of soccer again back into as an analogy here, the labeled data for the rules of a game of soccer will mean that in what condition a goal is happening, in what condition a free kick is given, in what condition a penalty kick has been offered. So these are parameterized and labeled, and from there the system will come to know that yes, if this situation matches, it is this event. If situation this matches, this is that event, and so on. So data are not always labeled as you collect, because these have to be labeled by human expert or expert with certain expertise about the domain. So therefore, what is happening in real life, the data is not labeled, but from there on, for machine learning purposes, labeled data sets are prepared. And once this prepared, this means we have some y as a function of this axis, such that which is conditioned with respect to the parameters theta, and with some epsilon j, where it is representing the noise after training, and it accounts for some possible inaccuracies, which may be due to corrupted measurements and faulty annotations. Now, always this possibility exists that doesn't matter how much care is taken, they are always going to be possible. It is going to be possible there are some errors are existing, or maybe that some real world scenario will not be matching accurately to a data which is stored and on which a machine learning system is trained. So therefore, there is going to be some kind of inaccuracy, and that is represented this epsilon j, and which is required to be minimized or rather optimized. So therefore, the family of functions capital F to which a particular model F belongs is called the hypothesis or the model class, and capital theta denotes the corresponding parameter space. Now here again, model by being the analogy of the weather pattern and predicting whether golf can be played or not. Then the rules, the decision tree which will be constructed based on, or rather, based on the rules, that is the disjunction of the disjunction of the conjunctions. So that will imply the model F. So that means model F is nothing but a set of rules, and all these rules are nothing but certain functions, and that these functions are basically a hypothesis. Why? Because a real world scenario for which the prediction is to be made is not, or rather may not be absolutely recorded in the training data. It may not be matching with some training data accurately, so it will go somewhere near to some existing training data. So a prediction will come, and which will be having some error involved in it. So that is how the job is to minimize this error to come to some kind of perfection. So now, in this scenario, broadly what we are speaking, then there are different types of machine learning techniques. There are many, but I mentioned three foremost ones which are presently in this scenario, which is supervised learning. Means the learning process in the software is supervised through some help, and this help is embedded in the training data. In the case of decision tree, it is the labels. So the last column of the parameter space are the label. So the moment data, every row, the data are recorded and these are read and computed against the values, then it will lead to a particular level, and that level is the training guide. So in the case of this, then in unsupervised learning, there is no such level. It is actually grouping the data. So supervised learning is one of the example is classification, another is regression, logistic regression, a nearest neighbor method. These are all supervised learning techniques. Then comes another learning technique when there is no help, no external guidance, means in the form of any uh, information about the data set is provided. Only the data set is there, and the machine learning system has to learn, and accordingly it has to group the data if the problem is of identifying the similar data that is in the form of some clusters. So unsupervised learning tasks include clustering, uh, finding dependencies among the parameters, how one parameter occurrence of a value in one parameter is dependent on the value of another parameter at a given point of time, maybe on time scale and other. So therefore, unsupervised learning tasks, two broad tasks, as I'm mentioning, is one is clustering, the other is dependency determination or dependency this thing. Uh, Dependency of one parameter with the other, which is also called sometimes association, also called sometimes finding frequent patterns. That means how many parameters are frequently depending upon each other and how frequent this dependence across the entire data set. So these are part of unsupervised learning tasks. Coming over is reinforcement learning, which is another learning technique, which is neither supervised, it is not unsupervised, but it proceeds in a sense of supervised learning, but it has got a feedback action in it. That means the learning and then trial and error technique, how good the learning is to be evaluated, and then the errors took place, where it happened, and these errors are to be provided as a feedback to the algorithm, and in the subsequent iteration it will try to incorporate those and then will make perfection to this reinforcement learning scenario. So here this type here is showing this different three kinds of situation. So machine learning goes in supervised learning. So here model getting trained with the labeled data. So there are classification tasks. In case of regression, just like we have to fit a straight line segment line through a set of data through regression technique within the range. Then grouping the data means clustering is similar. Finding the similar data points or data set, data elements in a large data space. So, and then grouping them together. So in this case, what we do, if we consider each of the data object belongs to a particular class. Class means a group. Suppose this region, it shows three groups, three regions. So this particular region has got certain dots in it. So are in these two. So why these are here? Because these dots are similar in certain way, and as determined by the program, the algorithm, and they are grouped together. So what is done here? Their similarity has to be calculated, and their dissimilarity as well as calculated. So once you calculate the similarity by using some metric, then the close they are, they will be getting into one of the groups. And likewise, the ones which are not as close as this will belong to some other group, but they are within them, they are close. So here, what we are doing, if we call each of the group as a cluster, so here we are maximizing or the intra-cluster similarity and thus minimizing the inter-cluster similarity. So similarity between two clusters are minimized if they are in different clusters, and the objects which belong to one cluster, their similarity is maximized. So different kinds of algorithms are there. Like in case of clustering algorithm, the most famous algorithm is k-means algorithm, which is for numerical data. And at this moment, what we can say is that, so in 19, after that, such survey has not been done actually. Around 1910, 2010, 2008 to 10, during this time, ACM and IEEE combined together to uh, conduct a survey, and in order to enlist top 10 algorithms for artificial intelligence, machine learning, and data mining. So this particular algorithm, K-means, was one of the top 10 algorithms according to the survey then. So was the algorithm developed in 1996 for association rule mining for finding frequent patterns, again an unsupervised algorithm called a priori algorithm. It is also enlisted as one of the top 10 algorithms, and similarly in others. Then, of course, we are into reinforcement learning scenario. Here, what we have, the environment is provided with the data. So the model is to be trained. So what we talk about model agent. Now, agent is basically an AI terminology where it is in terms of, algorithm. It is a set of functions which will help in taking decision as well as processing the data. So the AI agent and the machine learning agent is representing the model, and it is providing, accepting the feedback, going into a training loop. This feedback is taken back to the environment, and this loop continues for iterative process, and the uh, learning objectives are fulfilled in a better manner. So this is the three class of machine learning types in classical domain. And supervised learning, as we have already mentioned, it deals with label data, and the goal is to train a model such that it can produce an appropriate output Y for a given input X. And this input X is not part of the label data on which the data is trained. So in case of supervised learning that we have here, you see on the left, of course, these pictures, they can be done in case of images as well. So on the left, we have got certain different kinds of objects like vegetables, and the model training goes on happening. This level data is training data. So this training data, when executed repeatedly and the model is perfected, then it is able to classify the data as different types of vegetables. Now, these levels are coming actually while this training. This is the levels which are stored in the memory, and these levels are used while training the data, this data. So these data are used by using these levels, and these levels helped in identifying these images. And accordingly, once this identification has been expressed in the form of the rules, which we call the model, then this can be applied to a set of test data. So this data is not part of this. This is a new one. So the size and shape and the color and all that of each of the object here can vary, but still it will be able to predict based on the level of training that it has received, and accordingly this classification is done. So this is supervised training and supervised learning, and happened through this. Now, contrary to this, the unsupervised learning, as we have mentioned, in here it works with unlabeled dataset X, see, and aims to uncover the latent or inherent structures within a given dataset. That is, it is like the spectator who doesn't know how to play football, but observing repeatedly and able to identify the rules of the game. The examples include clustering, higher order correlations, or relational dependencies among the parameters, and so on. This scenario shows again the same unlabeled data, but without the help of the labels. It has gone to an interpretation situation. This interpretation is no longer a supervised interpretation, rather this interpretation will have to be formulated algorithmically based on the parameters involved in these objects. And these parameters could be belonging to its physical as well as other, nutrition and other parameters put together, color and everything, appearances. And based on shape, color, everything, and this interpretation will be submitted along with the data into the algorithms. Algorithms will be repeatedly executing the data set to finally produce some output. And you can see very well that there is in this case, the data is perfectly clustered, grouped. However, here in both the thing, we did not show any kind of error, means 100% accuracy has been provided, but it is not so always. There can be always a chance that one of the other kind of vegetable get into the box of another kind of vegetable. So that is likely to happen. And that is where the accuracy, that epsilon j comes into picture, and that has to be minimized. The error has to be minimized in this scenario. So now over to reinforcement learning. It's a type of supervised learning, of course, not purely supervised, but that receives feedback in place of label. So based on such feedback, reinforcement learning methods tune models that are typically intended for decision making in a feedback situation where current output may impact the next output. It is more important in game playing situation because, as we know, as a human, a player, when he gets experience more and more, his game playing ability also getting more better and better and become perfect. So similar is the objective here in the thing, that is learning from errors. So that means it is learning happens in such a reinforcement situation is a guided trial and error procedure in which a software agent is in some state and it decides for an action and which leads to a successor state. Means it will provide a feedback, this action, and then the game state will change, the learning state will change to a successor state, and only then subsequently it finds out that if a sequence of actions had a desired effect. Means it will have to be measured how perfect the learning has taken place and it is desirable or not. So this is actually a delayed feedback mechanism, and it is used to adjust the action selection mechanism by dynamic programming approaches. This programming, that is the feedback which it is receiving through the state of the game, current state of the game, and then sending back to change the parameters in the dynamic situation as the model is getting trained, executing. So therefore, the approach here is called dynamic programming approach, and over the time, the agent also learns which action to perform when in order to achieve certain long-term goals. Like the agent has to decide that if it has to provide a feedback to the learning loop, then it has to select that which action it is going to put into feedback path. If a similar situation happens again and again, there is no point in setting back again and again the same situation. So it has to be able to identify and judge that the appropriateness of a feedback action to be provided. So this is the job of the software agent, means AI agent in a sense. So in this sense, this is a mixed form of raw data here. The environment is here agent, and the algorithm and the selection of the algorithm the agent has to do. The environment is accepted as an input, and the reward is the measure of the perfectness through a reward function, gets to the agent evaluates how good it is, and again decides for the loop whether to go ahead. And in this case, it is showing up a grouping of similar data. It means a sort of clustering or similar data or object putting together. So the output is generated as a result of this. So though here it is perfectly shown, but it may be mixed if the training and the learning is not so perfect. Now coming over to the near part is that in this machine learning scenario, now we are talking about machine learning in the context of existing classical scenario, but how this is equally applicable in quantum machine learning scenario, because quantum machine learning process is not going to deviate from this. Rather, it will be enriching or enhancing this process only in order to achieve the goals. So here the machine learning pipeline, what you say, that is the multiple stages which a machine learning process undertakes. First, of course, is the data gathering collection and the balancing of the data. Means collected data will have certain noise and all that are there. But when you talk about, I mean, uh, supervised or unsupervised learning, the because as the data is in our hand and this data is for training the system, so therefore we should be well versed about the data and its nature. So therefore, if we train the data which is unbalanced meaning if we have a binary decision to be made, yes or no, that means number of yes data objects having a decision yes and the data object having decision no, they should balance each other perfectly. Same number of instances should be there ideally, but a near equal would be fine, like 45% to 50% on either side will do, because in reality we may not have such data always, and in certain cases, in certain machine learning scenario, we can never have a balanced data set. So there are techniques in machine learning domain for balancing the data set by artificially curating or data, means through simulation and then balancing it so that real data set can be balanced by using artificial data put together, and then same can be trained. So mean to say that collected data may not always be balanced, and it may not be possible to balance also in certain real scenarios. So in such a situation, there are techniques by which the data can be balanced, and the balancing should not be exactly 50-50. It may be close to that. Then comes into the data pre-processing stage. Pre-processing involves multiple actions actually. Removing the duplicate data, missing data, noisy data which are not actually as per the structure which is required to be in, and so on. So if a floating point data is required, if there is a complex data available, like string, non-numeric string, then this kind of data has to be filtered out. So data pre-processing has basically involved data cleaning, data integrating, then removal of noises, removal of missing values, and all that. So there are different techniques for doing all this. Then comes the fourth important step. Once the data collected, balanced, pre-processed, and more or less ready for computing, then the data has to be split into two disjoint subsets. Normally, 80% and 20% is recommended. 80% data is kept into one subset, which is going to be used for the training data, used as training data. That means the machine learning algorithm will execute on this training data repeatedly with variation of the parameters, adjustment of the parameters, as you mentioned, and it will try to get the near perfect classification with the help of the labels into it. And the second 20% that is being kept aside, it can be 70-30, 75-25, and so on, but should not be 60-40. Reason is, if the training data gets smaller, then training will never be perfect, because we should be able to give more and more wider representation to the data for training. So the second component will have the data, and those will be used for testing the training done by the program. So in this case, the second set, 20%, will also have the labels in it. But while the testing will be done, the labels will be deliberately removed. Label column will be cut aside, and the data without the labels will be provided to the model that is being produced as a result of the training by the ML algorithm. Then the test data will be classified and the classification, and it will be classified with the help of, it will generate the labels for each of the instances, take one by one, and then these classified labels by the machine learning algorithm will be compared with the original labels which were kept aside, and then we'll be able to judge how good or bad the training is. If it is not suitable, in the sense that its training accuracy is bad, or it is extremely good in other way, we do not expect 100% training results because there is going to be error all the time. So then the parameters are subjected to again readjustment so that certain level of accuracy is achieved and this is optimized. So this is the purpose of splitting the two disjoint subsets. Now comes the concerns. In the entire process of training, what kind of mathematical model is to be selected for a given problem? Like classification can be done through decision tree, entropy-based one, can be done through mathematical models of Gini index and others, can be done through logical regression, logistic regression, or linear regression, non-linear, and many other. So which kind of mathematical model, in this case, mathematical theory, will be fitting to a given set of data as well as the objective? This is to be decided by the human. So in this case, the current general recent trends are, while doing this is also part of the data machine learning pipeline, because while selecting the models, overly specified models are required to be avoided, because these models will not be fitting into the most of the scenario involved in the, encoded in the data. Rather, it is advised that very general and widely applicable models are to be undertaken, like as on now deep neural network, DNN, or for deep learning, or for image and all kinds of data, CNN, and so on. We can also have random forest. We can also have probabilistic models like Bayesian models and many others such that. So there is so many. So now once again, every model, every technique will not lead to same result. There are variations. So these are other concerns. Of course, these I'll not be talking about today on this scenario, but only to give a hint that just by merely selecting a particular model and executing data and getting an acceptable solution does not mean that the solution, the problem is solved in an acceptable manner. Rather, the ideal thing is that to be executing the same set of data by using different possible techniques, models, and then seeing what is happening and is there any consistency. And there where, this can be evaluated again by splitting the training and testing data, and so, because of which, and as a result of which, the involvement of, or rather analysis of the training accuracy and the error involved is a foremost requirement before finally deciding about a particular model to be taken into account. Next is the training phase. Once the model selection, mathematical theory, and the algorithm selection is over, then training phase begins, and as you mentioned, the parameter adjustment is the key here. And after that, the choice of the learning algorithm. Within the same mathematical model, there will be multiple learning algorithms. So what is to be chosen and all that. And already I have spoken thereafter, the validation means now using the test data for validation, how good the training is or has happened. So that is to be done by finally finding the accurate prediction with the available prediction with the test data. They can be compared, and accurately it can be calculated with various parameters, like true positive, true negative, false positive, false negative. These are 4 parameters. Along with these, the types of 2 different types of errors, that is type 1 and type 2 errors, and all this can be calculated, and accordingly, if these are not accepted in the acceptable range, then this can be further optimized. And once a satisfactory validation and has happened, Then finally, the ML systems has to be deployed for practice. So this is the complete ML pipeline, and this pipeline has to be implemented in quantum scenario. And this is the requirement as of now for quantum machine learning, for a quantum machine learning technology development. So therefore, coming to how to define quantum machine learning, it integrates quantum algorithms with machine learning algorithms, existing quantum algorithms for the new quantum algorithms with existing ML. It has to use quantum circuits for data processing, which is a very complex domain. As of now, quantum computing is not in a scenario in which we are performing with classical computing. It aims for performance gains in learning tasks. Whatever we have in case of classical machine learning scenario at this stage, obviously the idea is to gain performance in performance, and then the scenario is experimental, but it is rapidly growing. So quantum support vector machine, one of the variant of classical support vector machine algorithm. It is the quantum version. It uses quantum circuits for kernel functions. Here the data is mapped into quantum feature space, and the classification happens through maximum margin principle among the through the hyperplane actually. It promises exponential speed up in terms of presently, as the data grows, the problem get into the NP-hard region. Like we talk about the sequence mining or frequent pattern mining problems. This moves into NP-hard region with the rise in the number of parameters, the features otherwise. So therefore, in case of quantum computing, the ultimate gain, of course, to achieve logarithmic complexity for big data, which of course is a big dream. If that happens, truly it will be one of the marvelous things that can happen with computation with large, huge data sets. So a broad flowchart level of work is that state preparation followed by input classical data to encoding into quantum data, providing optimal classifier processes, then variational quantum computing based QSVM, quantum kernel estimation, QCV based testing, quantum kernel estimate based testing. So this is how the scenario is developing as of now. Now QPCAs, that is principal component analysis, another analog of this, It is components of a density matrix scenario. For it is having exponential speed up in low rank matrices as of now in quantum computing scenario. It is already providing in the present day computing scenario for low rank matrices, exponential speed up is achieved in this domain. So is in case of SVM. And this technique is used for feature extraction and noise filtering. So features means the parameters. So when we have a number of parameters in data sets, as I mentioned before, in a learning scenario, all parameters may not be appropriate because there may be certain parameters which are similar to each other. So such parameters need to be removed. So therefore, otherwise there will be, if the correlation among the parameters are high, then learning would not be appropriate. So such things are good through PC. So broadly speaking, this is a PCA scenario here. High dimensional data on the leftmost block here. So this is through the center points options like different dimension of variances are offered. So compute covariance matrix here, and these are the different steps. And finally coming over to this. So I'm quickly skipping because time is also nearing an ending scenario. So then quantum neural network scenario, how it could be like. So it is a neural network to be built on quantum circuits. It is to be parameterized the quantum layers. It can model complex data distributions. Hybrid architectures are often used as of now also, and so it's going to be in case of quantum scenario. Quantum circuit, again, it is going to be layers on a neural network. Parameters need to be updated using classical optimizers. Parameters adjustments now, this is the optimizer, what is called problem here in parameter adjustments. It involves gradient descent techniques or gradient estimation, parameter shift rule, and output measured and fed into loss function. So multiple steps, quickly I'm going through in this case. So blockwise, from input to output, these are multiple states of quantum neural network scenario. As on now, of course, with advancement, this scenario will be becoming much simpler, I guess, and has to be. So data loading, reprocessing, the measurements, training, and then the connected layers through which finally the output will be coming into the use. Next is variational quantum Eisensolver, that is called VQE. So it is for ground state energy of the Hamiltonians and the hybrid quantum classical loop and trial state error prepared by variational circuits and used for quantum chemistry. So I am not fully experienced with this, but this is happening at this stage. So the data, chemistry data are required to be, data related to the chemistry is to be put into one of the options that we have in case of variational quantum Eisensolver. So idea is broadly the similar, like quantum state preparation followed by different modules, showing in the Hamiltonians going into the classical adder, and then the expected values comes out, and then the finally going to feedback loop broadly. Now, future challenges in QML. Of course, everything is future. We are getting into a small reality at this moment. So quantum noise and decoherence problem, how to control it, minimize it. Error correction. As of now, there is a lot of things here to be done. Qubit counts limits the scalability, and scalability of the quantum algorithms are basically getting limited to qubit counts, and at the same time, algorithm design complexity that we have, that is very much there because it involves so many complex levels as on now. So to give an example of this algorithm design complexity, as I talked about, one of the association rule mining, of course, quantum classification algorithm has progressed quite in a good way. Quantum SBM is also has taken good steps, but till 2024 December, since 2016, the first paper that I have seen in this domain, that is in the domain of computing frequent patterns in data sets, means how one of the parameters of a data set is related to another parameter in terms of its occurrence and presence in the entire data set. That is done through, classically, many algorithms are there in machine learning and data mining parlance. A priori, then variants of a priori algorithm followed by other algorithms here. So these classical algorithms are at present able to compute hundreds of terabytes of data on, of course, HPC level. But in 2016, only a 2x2 matrix representation of such a transaction data set has been computed. And thereafter, the next improvement of the algorithm done by the same people has come as a quantum implementation with speed up in 2024. And meanwhile, I have read another report in which they could achieve two things for a 4x4 matrix. Means four what is called parameters, that is features, and 4 data instances, 4 rows in the matrix, 4 data sets, 4 data elements, and each data element has got 4 what is called parameters. And in that they are trying to do two things. One is optimizing the number of qubits requirement, and as well as the going to that. So this is what has happened in case of frequent pattern mining. which is a task in unsupervised learning scenario. Clustering, of course, also has good progress made. So this is the scenario in which we are in actually in quantum machine learning. So I try to combine machine learning in both ways, try to, in this presentation, move back and forth between present day classical machine learning and what could be the possibilities on quantum machine learning without throwing much light into the deepness about the algorithms, but about the nature and the context in which the problem has to be solved. And what are the challenges that we have ahead in case of quantum computing. So I have just come to fully the closure of today's presentation, and hope I have been able to explain certain concepts that I planned. And thank you one and all for having the patience to hear me in this situation.
Thank you very much, sir, for your insightful and highly informative session. Now the session is open for questions and discussions. Participants are requested to unmute themselves and interact with the speaker.
Hello, sir.
Yeah.
I have a question.